Okay, hello and welcome back to Data Science Castnet. This is lesson 6 of our AI art course, and today we're going to be looking at transformer models for modeling sequences, and we'll be revisiting the paper that introduced VQGAN, but looking at it in a very different way to what we did in lesson 3. So as before, this is the kind of shorter, more formal version of this video. This lesson was also given as a live stream. So I'll link that down below as an unlisted video or a Twitch link. And if you prefer a more conversational style and a longer video that you can follow along with, then you can go and check that out. But I'm going to try and condense what was in that video into this one so that you can also just use this going forward. Okay, so if you haven't already, you can make a copy, save a copy in Drive of the lesson notebook. Unlike some of the previous ones, this is much more just a few demos, and we're going to be doing a bit more talking and a bit less really diving into the code. But it's still fun to play around with. So without further ado, what is the sort of inspiration for today? Well, one of the main key sort of drivers was this dall-e system. So obviously dall-e 2 has just been announced, but just over a year ago, January 2021, the original dall-e model was announced, and at the time, much better than anything anyone had seen, and kind of blew our collective minds with the things that it could do. And in some ways, it's still a really good model. Unfortunately, this was never released, but at least it inspired a whole bunch of open source replication attempts and other research into this kind of image generation. And the way they did that was with something called a transformer model. So the goal of today is to just kind of get familiar with what's going on here and see how we could build a system like this ourselves, or at least get familiar enough with the building blocks that we can interact with one that someone else has trained. So that's the core idea. If you've been following what's happening in the open source community, you'll have noticed there is dall-e Mini, right? So this is an open source kind of smaller version of the original dall-e. It's actually ongoing training at the moment. So I linked this in the lesson. Feel free to type in your own prompts. We had some people sharing their results in the chat. And then there's also a much larger open source dall-e Mini, but it's 2.6 billion parameters, so not so many. That's currently training, and so later on we can take a look at the training logs there. But first we want to understand what is happening with these models. So go ahead and run the setup section. I've already run this. Shouldn't take too long, that first bit. And so we're going to start out with talking about what is a transformer model and what is this task that we're doing. And I'm going to try and not get too stuck in the weeds. So we're not going to dive deep into the different architectures and their relative merits or anything like that. But I know for those of you who do want to go deeper, I've linked a whole bunch of resources here that you can use to dive in the illustrated GPT-2, for example. Really excellent in-depth visualization of what exactly is going on. But we're going to do a bit more of a higher level overview. And so to get us kicked off, I thought first of all, we can start with a demo, right? We're going to attempt to generate some Shakespeare. And then while that's training or while you're exploring that, we're going to come back and sort of say, okay, what is happening here? So this is all based on this MinGPT library, right, by Andrzej Karpathy, a name you might recognize from self-driving at Tesla, for example. Does lots of really good software development. And a lot of this first example, the Shakespeare example, comes straight from his demo notebook in this library. So really highly recommend checking this out. Go and read all the code, right? It's very accessible, very well explained. But we're also just going to be playing around, and this is going to be our transformer architecture that we use for the demos in this lesson. Now there's many different implementations. You can see his sort of little demonstration here is that this is a nice mini concise library that's going to give us a lot of that power without all the bells and whistles. So that's why I chose to go with that. Okay, so our goal here is to build something called a language model. We would like to take a sequence, in this case a sequence of words or letters, and predict what's going to come next. And this is an interesting task because to do this well, and this is something that humans can do well, we have to know a little bit about the world. So for example, we have a string, the cat is eating, and then we want to try and decide what might be likely to come next. And to do this, the model has to learn something about what cats eat, right? And so the next word that might come might be A. And then the type of model that we're training here, we're going to call it an autoregressive model. That is, we can generate even more predictions by feeding in past predictions. So we take this input, the cat is eating, we see what the model predicts might come next and pick one of the likely options. Then we feed that whole string back in and rinse and repeat. The cat is eating a mouse. And we can do this as much as we like to generate a longer sequence. So our setup for this is going to be relatively simple. We're going to take in a maximum of 128 tokens. And in this case, our tokens, right, our things in a sequence aren't going to be words. We're not going to have some fancy vocabulary. They're literally going to be individual letters. And if you want to dig into exactly how this works, you can check out the dataset definition here. We're going to take in all of our data, right? In this case, a bunch of Shakespeare. We're going to get all the unique characters, and that's going to be our vocabulary. And then we're going to create a mapping from those text A, B, and C to some numerical representation, which we can then feed to the model, right? So that's what this is setting up. And then when it comes time to grab our data, we would like to train the model on this forward prediction task. And so we're going to create our X and Y, X being the input to the model, Y being the desired output. And if you examine the code, or if you go and check out the example, our X and Y are going to be the same, except that Y is shifted forward by 1 token. So you can see X here starts 18, 47, 56. Y starts 47, 56, and carries on. And then X ends 53, 1. Y has 53, 1, and then this additional extra token, 42. So we could set this up in a few different ways. The neat thing about this particular sort of implementation is that this is going to give us some extra benefits come training time that are documented in the code, because it's going to not only train giving this whole sequence and expecting this whole sequence with the extra token, it's also going to simultaneously train giving up to some token and then trying to predict one additional token. So there's some optimizations under the hood, but the core idea here is that we've got this sequence, and in this case, it's just a sequence of numbers representing individual letters, right? A space C space A T. These have been turned into numbers, and we're going to try and model the sequence. And you'll see as we go through, this is the core of what we're doing when we run a transformer model. It's just that those tokens don't always represent individual letters. They could be individual words. They could be proteins in an amino acid, or as we'll see, they could be components of an image. But anyway, this is our first little demo. We're going to create this GPT model, and we don't know what these parameters mean yet, right? What the vocab size, block size, number of layers, number of heads, and our embedding size. But that's okay. Run this code, and then you can run the training. And now if you've done previous lessons, you know, we usually write our own training loop, right? For batch and data, zero out the gradients, calculate the model outputs, calculate the loss dot backwards, optimizer dot step. So don't be a little bit put off when you see this in a different format. If you go and check out the MinGPT library, you can go and read trainer.py, see what this class looks like. And if you dig in, you'll see that it's some extra sort of features and fluff. But at the core, going through our data, calculating the loss.backwards, optimizer.step, right? And there's some extra things for saving the model and changing learning rates and so on, but the core idea is the same. Okay, so you can run that and train, or because this takes a while, you can also run this cell here to load a trained model, which I ran using this exact code. So if you just want to skip ahead and play with the model, you can. So I've already run that, and we can sample, we can give it in some particular context, right? So this would be the first few tokens. And then we can sample from the model, right? We can feed that in, see what the next prediction is, feed that all in, see what the next prediction is. And for a model that's trained from scratch in relatively little time, right? I think it was half an hour or an hour. It starts to look fairly close to Shakespeare until you look too closely, right? It makes spelling mistakes. It doesn't really make sense long term. But on the other hand, it really does generate stuff that looks plausibly like Shakespeare. And so this is kind of the magic of these transformer models. They're able to take sequences, they're able to learn rich patterns in that data, and produce plausible continuations of those sequences. So that's great. You're welcome to play around with this. I can highly recommend substituting in the training data here is a bunch of Shakespeare, but you could put in your email history or sort of more modern books, etc. It can be really fun to mess around with. And then obviously there are more advanced approaches to this where you use a larger vocabulary and a special tokenizer and so on. There's a Hugging Face book and some resources linked above. But this is a fun first little demo, right? Okay, so before we dive even further or try and understand how this relates to the course, making AI art, which is usually imagery, let's take a little dive into what exactly is going on under the hood. So what is this model? So transformer models were first proposed in this famous paper, Attention is All You Need, in 2017. And they took this relatively new idea, right? Attention had been around for a little while, usually combined with something like a convolutional neural network, or a recurrent neural network was the latest greatest thing for especially text processing. And they said, what if we do away with the rest of those architectures and try and lean on just attention? And of course there was some snarky comments of, well, you mean attention plus these feed-forward networks plus embeddings and positional encodings and all this other jazz. But the core idea was you could take this basic architecture, and I know it looks a little complicated when you don't know what any of this means, but a fairly simple architecture, and specifically this encoder block and decoder block, right, these two things on the left and right, you could stack these up. So this little NX here, you could put 5 in a row or 12 in a row or 80 in a row, right? It was a very reconfigurable architecture, and it was just copying and pasting the same thing, and yet it was able to do much better than more traditional approaches on a wide variety of tasks. So this worked really well. As we've seen, transformers are now pretty much dominant in a lot of deep learning arenas. But since this original paper, there's been some modifications. So rather than having this encoder-decoder model, we've seen encoder-only models like BERT, decoder-only models like GPT-3, which seems to be the direction things are moving. Well, even the original GPT and the one we're going to be using here. And so these models kind of do away with this encoder-decoder sort of multi-stage thing. And instead we end up with just a stack of these decoder blocks, right? Each one looks the same. We're going to take in a sequence and then we're going to have a stack of these decoders. By the way, this illustration is from this illustrated GPT. And then how many stacks there are in that model is one of the parameters that we can tweak. Okay, so very, very neat architecture and yet very powerful. So let's dig into exactly what's going on and some of the key concepts. And for each of these, I'll just be giving a very high-level overview. But again, that material linked earlier is a great place to go if you'd like to learn more. Okay, so key number one, embeddings, right? We have this sequence of tokens, and you remember for the text, we represented these as numbers, right? These are like individual characters in the vocabulary. So 47, 56, etc. So we want to turn that into some sort of meaningful representation. And we've talked about representation learning before. And so one of the ways that that's done in these models is with so-called learned embeddings, right? And this is just a big table that every row might be a particular item in our vocabulary, right? Say a word. So the word boy or prince or king, those would all be different entries. And then the embedding for that word is some size, right? 512, or you can sort of define that. And that's one of the parameters of our model here, this n embed, right? How large is our embedding? That's going to be some numerical representation, right? A vector of size 512. And that's going to try and capture some meaning with that word. And originally these start out random, and over time these embeddings are learned in such a way that words that are similar in meaning, right? Maybe a word with a capital versus a small letter, boy versus man, child, or whatever, king and prince, those might end up relatively close in this embedding space, whereas widely disparate concepts might get very, very different embeddings. So even without the rest of the model, these embeddings are able to capture quite a lot of rich semantic meaning, right? Dog and puppy are similar, and there's a whole lot of research as to what the relationships in this kind of learned embedding space are like. But this is just what we're going to be feeding into our model. So before we even get to the main part, all of the self-attention and so on, we've transformed a sequence of tokens, robot must, into these rich embeddings. And these are learned, so it's just a set of weights that we can update with gradient descent. Okay, so that's key number one. Number two, positional encodings. It helps to let the model know where the word that it's looking at is in the larger sequence, right? And so we add, you can see it in this diagram here, this positional encoding is just a way of representing that. And so a simplest positioning encoding might be a single number 0 to 1, where 0 means the start of the sequence and 1 means the end. In practice, we use more complicated positional encodings, right, that have, sinusoidal variation or exponential variation that kind of better capture where in the sequence something is. And I point out here there's been some recent sort of papers exploring what happens when you leave this out and saying actually these models can still do okay at a lot of tasks without this positional embedding. But for now, at least, it seems to be something that generally helps. And so that's part of most of these systems is encoding our position somehow. Okay, so that's the two things that happen before we get to our main part of the network, these stack of decoder blocks. We're encoding the inputs into these embeddings, and we're adding a positional encoding as well. All right, and then number 3, attention. This is really the core. If you want to go dive deep into these illustrated articles, you can find the section on attention. But the core idea here, and I like this kind of metaphor for it, is that we take the current word that we're looking at, right? And in this section here, it's this word it. Through the mechanism of attention, we're able to combine that idea, right? Try and understand the representation of this word with relevant other parts of the sequence, right? And so in this case, this it, we don't know what it refers to, but this masked attention is able to sort of attend to the relevant parts of the sequence and combine the information contained here with this to feed forward into the next layer. So how that works can seem a little bit complicated, but the core here is that the model is learning some matrices of weights, right? Some parameters that define these operations, which let us compute so-called queries, keys, and values. And these are what's used in the attention layer. And so when we're looking at a particular word, we compute the queries, keys, and values. We're going to say, okay, it's like this this little metaphor here. We're going to go with that query, and we're going to score how much the different the other words in the sequence relate to it, how relevant they are, and then we can kind of combine all of those according to that score. So that's a very hand-wavy definition. I know you can go and check out the Neuromatch content linked in the intro. Has a really good, implementing it from scratch kind of introduction to attention. But for us, it's enough to know that this is a really neat mechanism, right? And it's able to, rather than just processing one item at a time, it's able to attend to different parts of the sequence, even for fairly long sequences. And this is the key advantage that transformers have over a lot of other models, right? They're able to take into account these kind of interdependencies within a sequence, and so that gives them much more power in terms of modeling those sequences. And then we have this extra waffle of, okay, it's masked self-attention. What does that mean? That just means that we're doing this forward task, and we only want to look back at parts of the sequence that we've already seen. We won't let the model look forward. There's other types that don't have this masked self-attention and instead want to, maybe process the whole sequence at once or from different directions. But for our kind of basic task here, our language modeling sort of autoregressive task, masked just means it's only looking backwards. And then multi-headed attention, some of these models will, through some reshaping and splitting operations, they will actually train multiple separate instances of attention. And this sort of hand-wavy intuition is that different attention heads can learn different key concepts, right? And so it's just kind of hedging our bets, splitting out that self-attention across multiple heads, and that's the n heads parameter that we passed into our model here. Here we go, n head is equal to 8. That's just giving it effectively more chance to learn more complicated things, right? So when we're talking about scaling these models, we can add a larger stack, right? So GPT-2, the small model was, I think, only 12 decoder blocks stacked. The largest one was 36. We can also increase the number of heads for each self-attention, and we can increase the embedding size and the vocabulary size and so on. Okay, so that all sounds fairly complicated, but the core thing here is that every part of this operation, right, the attention with the keys and the values, the sort of processing by the next neural network to pass it on, the embeddings, all of that is just learned matrices, right? Weight matrices, so parameters that we can update. And we know from last week, although we've never encountered a model this complex, if we can define something that takes in some inputs, produces some outputs, and what it produces is based on some parameters, and everything's differentiable, then we can update those parameters using gradient descent to try and reduce our loss, right? So these models might seem kind of crazy and intimidating, but we can build on others' work to create one as simply as calling a single function, right? Model is equal to GPT with some configuration, and we know that this is going to give us back something with, in this case, 2 times 10 to the power of 7 parameters. But all of those parameters are things that we can now update in a training loop to ideally learn the kind of behavior we'd like it to learn. So I know that's quite a long exploration, but hopefully that gives you just enough of a mental model that we can now treat these as kind of like this really good generic sequence modeling tool, right? If we've got a sequence of tokens and we would like to learn patterns in that data and generate continuations of the sequence, then a transformer is our friend. It's got some wonderful different tricks up its sleeve to let it do this really well. And we can lean on that and leverage that in all sorts of ways. So that's our intro. And now it's time for the fun bit, because we would like to now go back to the question of, okay, this is great and I can see how it can generate some Shakespeare, but we don't want to generate Shakespeare, we want to make pretty pictures. So now enter part 2, going back to VQGAN and rereading that paper with this new tool in our heads that says, hang on, if we can represent something as a sequence of tokens, we can model that with a transformer. And that's exactly what this paper does. Taming Transformers for High Resolution Image Synthesis. Very excellent paper. And in it, this is the core of their architecture here. They show a couple of different components. So the one that we've looked at before was this VQGAN, right? We said we could take an image, we could use this convolutional neural network encoder to shrink this into a compressed representation, right? Where every patch in the image had some latent vector associated with it. And we could decode that back into the image. We sort of hand-waved away the fact that they did this quantization step. But now it turns out this is going to be really useful, because by applying this quantization operation, they take these continuous latent representations and they map them to a fixed code book, right? So they have some vocabulary, some number of codes that they use, and each one of these corresponds to some particular vector in the latent space, right? So now we've gone from our image to this compressed representation that's still a lot of numbers, to just a sequence of codes. So this dog comes in and we get 1, 42, 3, 3, 94, and so on, right? And so this step here means that we now have a sequence of tokens, which, as you can see in the diagram, we can now feed into a transformer. And we can also take that sequence of codes and through our decoder, turn it back into an image. And we mentioned that this discriminator here was just used during training to make sure that these images looked as realistic as possible and that the system sort of trained well. Okay, so that's their sort of setup. Really, really neat trick. There's lots of fun exploration in the paper as to, how small can we go? How many codes do we need for accurate reconstruction? But this key idea that we can take an image and we can turn it into a sequence of codes, each one for a particular patch of the image, and then we can feed that to a transformer, that's really powerful. And so this paper shows a bunch of different things that you can do with that, right? We're not going to dive in too much into the scary sort of maths, although it's not actually that bad when you take a look at it. But instead, I'm going to skip ahead to some of their results. So what can we do if we can represent an image as a sequence? Well, number one is simple auto-completion, right? Just like we did with Shakespeare, we feed in O Romeo, and then we have it continue generating. Here, they feed in the start of an image, right, the top half, and they have it continue generating that image. And actually, that's what we're going to do in this next section of the paper, of the notebook, right? We're creating a model just like before, but in this case, our data set is a sequence of tokens, but now they're codes from VQGAN, right? If you check out the data set here, you'll see we're opening the image, we're encoding it with VQGAN, and then we're getting this like list of tokens that now, just like before, Y is one ahead of X, but instead of being individual letters, these are now individual codes from the VQGAN codebook, and we can feed in half of an image, right? So here, the top of this, we're feeding in 128 out of 256 patches, and have it try and auto-complete the rest. So you're welcome to run this, set this going. In fact, make sure that you run the additional setup probably now, so that by the time we're done looking at the paper, you're ready to experiment with this. But this is a really neat application in and of itself. You can see in the paper, it's able to generate fairly plausible continuations of an image. And you can imagine a kind of more simplified version of this would just be, I'd like to just erase part of the image or fill in part of the image that I don't like. You could feed in all the sequences up to the part that you'd like to replace and then have it generate some plausible in-painting. So that's one potential application. But the next sort of key idea from this paper is that our sequence doesn't necessarily all need to come from the same place. So if we feed in a sequence of tokens representing, for example, a depth map, and then a sequence of tokens representing an image, and feed this type of sequence through a bunch of times, the model is going to learn that when I'm generating the image part, I can look back at the depth map and use that to inform my predictions, right? Because this is all one long sequence, depth information and then image information. So when it's trying to fill in the image, it can look back at the depth, right? The so-called conditioning information. And then it can try and generate plausible outputs based on that information that we give it. So you can see here, they fed it a bunch of labeled images, right? With different classes, and then the image that corresponds to. And now come sampling time, we can feed in just the labels and try and get out some images. Same thing with feeding in a pose and getting out an image, even feeding in just a class, right? A label like frog or cat or German shepherd, right? Encoded in some way as the first token in the sequence, and then continuing the sequence with the actual image, they can go and try and generate some class conditional outputs. So a really wide range of tasks that you can do. They have a whole bunch more examples in the appendix, but it's really neat because if you look at these landscapes here, they feed in as they're conditioning a map that effectively has sky, some vegetation, and some water, right? And then they have it go and look at that as a sequence and then try and continue that sequence with the image that should follow it. And they get these sort of multiple variations of amazing auto-completions of that sequence, right? So really, really cool. In the GitHub repo, they link to some notebooks that you can experiment with. So let's find that here. Yeah, this landscapes from Flickr. You can run that in Collab and explore the code and see if you can find the bits where they're, taking a mask, turning it into a sequence of tokens, feeding that as the context for the model, and having it autocomplete. So really, really powerful ideas. If you want to go and watch the live stream, I think we talked a little bit more about reading through this paper. But this core idea is that we now have the superpower, we can represent an image as a sequence of tokens, and we can do the same for a conditioning image or a mask or a label. We feed this as a sequence in and then have the model continue on from there. And they do tricks like applying this in a sort of sliding fashion, almost a convolutional fashion, to take a model that was trained on short sequences, right? Maybe 16 by 16, so 256 patches. And they can generate a much larger image by effectively feeding the model one block at a time and having it complete. So really, really cool paper, really, really impressive work. And we're going to build on that now to say, well, what else can we do, right? These examples that they showed here, conditioning just to finish the second half of an image, conditioning on depth, or conditioning on labels, these are all well and good. But the final kind of next step in our notebook and in these experiments is going to be trying to say, well, what if we just feed in text, right? We'd like to imitate this fancy dall-e model where we feed in some text and then have it autocomplete the imagery. And so this is where we're going to get to at the end of the notebook. And how are we going to do this? We're just going to smush together our Shakespeare example and our image autocompletion example, right? So I don't recommend this as a kind of perfect implementation. This is very much just for demo. But if you want to check it out, we are doing the most simple possible encoding of our text, right? The letter A gets turned into a 1, the letter B into a 2, or 0, 1, 2, 3, and so on. We have a special number representation for anything that's not in our very limited vocabulary. And then we have another special token that's going to be the sort of end of sequence token, right? So VQGAN, the model I chose to use here, only has a codebook size of 1024. So combining that 1024 plus our encoding of the text, that gives us our full vocabulary. And if we take a look at the data here, so this is, actually I should probably start running this. So let's define our data set, load in, okay, this is my fault for restarting the notebook and so on. Okay, maybe I didn't run this additional setup. Okay, so I'll wait for that to load. But yeah, so while we're doing that, I'll scroll back down and try and load this again. Okay, so our data looks something like this, right? We start out with some encoding of the text, and you can see I've just mapped the text. So the first 1024 sort of items in our vocabulary are VQGAN image patches, and then the next 53 or whatever is text. So we start out with some text, and this comes from the label of the image. Our data set has captions, and then we follow that by 256 VQGAN encoded image patches, right? So we're just smushing together the ideas from Shakespeare and the ideas from that previous section where we were trying to autocomplete images. We're saying we can represent both chunks of an image and letters in a piece of text as numeric tokens, right? So we can feed that in as a sequence to this transformer model, and then we can create and train that model, and hopefully it learns how to predict the next token in this kind of sequence. And so it's going to take a little while to download VQGAN and so on. Apologies for that. But ideally, we can already skip to the outputs. We're going to train for a short while. Now, you can try and train this yourself. Do mess around with tweaking the parameters, creating a large model and so on. But spoiler alert, it's going to take a little while to get anywhere useful. So again, I've trained this model. In this case, I trained it actually overnight. So I think 12 or 15 hours of training on a cloud instance somewhere. And I've made those weights available. So if you inspect this code here, it's going to go and pull down, this checkpoint that I've saved earlier using something like this, torch.save, all the model parameters. So we can go in and load that model once the code runs, and then we can generate some images, because just like before for the Shakespeare, where we said we're going to set our context as just the encoded, first sentence and have the model complete from there. In this case, we're going to take our prompt. We're going to encode that, right, as now the sort of same, so that it's the same vocabulary as our model. And we're going to feed this in as our context. So this X here is running through this encoding of our prompt. And then we're going to say, okay, I would now like to sample the next 256 tokens with the model. And we'll go and convert those back into our VQGAN patches, right? We'll take those 256 generated outputs and we'll turn that back into an image with VQGAN and see what the results look like. And you can see they're not perfect, right? They're not going to compete with anything state of the art today. But on the other hand, we asked for a mountain landscape with a blue sky and green hills, and you can see some bluish skies and some greenish hills, and this looks fairly mountainy, right? The other examples up at the top of this section, very cherry picked, because this is actually not a really good model. But on the other hand, when you step back and appreciate what's going on here, we've taken a model that hasn't seen anything before, right? This is trained completely from scratch, and we've taken some images with captions and we've encoded them as a sequence where we have the caption and then the image, right? And just with these sequences, we fed them through the model and trained it to try and understand how to predict the next token in this kind of sequence. And we've given it, a few 100,000 examples. And in doing so, it's learned that when it sees a sequence that starts with some words, or actually in this case, just letters, talking about mountains or oceans, that the tokens that are likely to follow, the image tokens that are likely to follow, probably look something like sky, ocean, hills, right? And when it's generating these, it knows, okay, if I've made a bunch of sky and then I've started doing green, I'm definitely not going to do sky again, right? It's more likely that there'll be more green grass after this. So it's able to learn all of these kinds of patterns in the data. And I know this particular one isn't very good. You can definitely play around with a trained model and find some cases where it's plain horrible. But on the other hand, it's kind of incredible that it's able to do anything at all. And if you took this example back 5 years and showed it to people and said, hey, just try this with maybe 1 million images and a little bit more training time, you'd blow their minds, because this is sort of on par or slightly ahead of what we had, 2015 state-of-the-art image generation from text, right? So it's kind of crazy, and that's the key takeaway from this whole lesson, is that we can represent text and images as sequences of tokens, and it just so happens that the transformer model is a magical tool for modeling sequences of tokens and predicting what's going to come next. And by combining those together, we get something really powerful. Now, if you look at something like dall-e Mini, right, they've done their work. Let's see. Right, we can ask it for something quite complicated, and it's going to hopefully generate some fairly plausible results. So we'll check that out shortly. Okay, so this is still running. I apologies, I thought I really had run the setup section already. But you're welcome to go around, play with this, share any amusing results you find in the notebook. Before we end the lesson, I'd like to just end on a couple of asides and then wrap this all up. So number one, this kind of model is really cool, but like I said, especially this second sort of section 3 model, it really did take multiple hours to get anywhere. And at that stage, it starts becoming really useful to explore things in a Colab notebook or whatever. But sometimes you want some more formal code for your actual training. And so that's where things like setting up to save checkpoints automatically, right? Like this min GPT library does. You can set it to, write those checkpoints every hour or every epoch or whatever you decide. Save that checkpoint somewhere safe. You can use cloud platforms to get something more reliable than Google Colab, right? Vast.ai, very easy to avoid overspending. You can put in $10 credit, rent an instance for 40 cents an hour with a really nice GPU, and set your model training. Tools like weights and biases for tracking progress and keeping track of model versions and so on, really powerful. So this is the workspace from when I was training this final demo, and you can see it tracks things like the loss, learning rate, etc. But also gives us, GPU utilization, which in this case, obviously my code is not very efficient. We could be doing a lot better. But you can also dive into, so this is the dall-e mini training, a much more fully featured report where they're keeping track of model checkpoints, they're keeping track of demo outputs, right? So if you scroll down here, you'll see explanation of what they're doing, but also some example reconstructions, some example, curves from their different experiments, right? What happens when we use a higher or lower learning rate? How should we train? How does this work over 40 hours of training? What do the results look like? So spending a little bit of time up front, and it's really very little code to add something like this to your training code, but it gives you a lot more insight and control and reproducibility. So when you're doing these longer experiments, I just thought I'd flag as a little aside, it's really worth spending some time setting everything up neatly, tracking it, and making sure that you're not going to waste 12 hours on a model that's not actually training at all, or that's not going to save, and you're going to lose all of that progress. Okay, so that final little aside out the way. What have we learned? Let's just do a quick final recap. So like I said, we have this modern transformer architecture able to learn very complex patterns and sequences of data, and we can represent all sorts of things as sequences of data. And so if we feed in a sequence that's some conditioning tokens, like a text description or a map of what we'd like the scene to look like, or a sketch, for example, and then train the model with sequences like that, followed by the images that we would like it to output, we can get a really powerful generative model able to take a diverse set of inputs and turn them into plausible looking images, right? So it looks a little scary, but it's all just matrix math. It's all something that we can use gradient descent to optimize, just like all of the other examples we've seen in this course. And so I hope that's kind of demystified it for you. I hope that you can go now and read the background for a project like dall-e mini, or skim the Taming Transformers paper, and see that this core idea here is actually really powerful. And even though I know at the moment diffusion models and so on are kind of stealing the limelight, this transformer-based approach to modeling images, really powerful, really useful, and I think going to be still showing its use in all sorts of ways going forward into the future. Okay, so that's lesson 6. That's a wrap. Thank you so much, everyone, for coming along on the journey. If you have questions or comments or feedback, I'd love to hear it. There'll be a link to the Discord in the AIAIART GitHub. So if you head on over to that, it should be linked from this video description and Twitter and everywhere else. There's a Discord link so you can come in and ask your questions. You're also free to reach out to me on Twitter or anywhere else and say, hey, I'm going through your lesson. I've got a question about, that thing you said about positional encoding or whatever the case may be. Come along, ask the questions, and yeah, I'd be happy to chat in more depth. But that's it. I hope you've enjoyed. Thank you so much, everyone. And yeah, I will see you next week for our long-awaited lesson on diffusion models. Cheers for now.